Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think yesterday we were discuss about the reaction of furan. What are the different kind of the reaction shown by furan? Specifically, furan is an aromatic compound. The reaction of furan undergoes electrophilic substitution reaction at two positions. And why electrophilic substitution reaction occur at two positions? The answer of that question we would obtain by knowing the resonating structure. We draw the resonating structure, and from that we got the answer why furan undergoes electrophilic substitution reaction at two positions. That we clearly understood by observing the canonical structure or the resonating structure, and the reactions given by that furan like sulfonation, Friedel-Crafts acylation, Riemer-Tiemann reaction, diisocoupling reaction, hydrogenation reaction. These are the commonly known reaction we have discussed in our previous lectures. So today what we are going to discuss? We are going to discuss the 5-membered heterocyclic compound, that is the second, which is known as a pyrrole. We will talk about the pyrrole, and as we know that pyrrole has a structure. Let's see here. This is a structure of pyrrole, which is a 5-membered ring. The common name of this pyrrole is common name of this compound, which is represented on blackboard, is common name would be pyrrole. The common name of this compound is a pyrrole. Now the systematic name of this compound, as we know that if oxygen atom, we can call it as a oxa. If nitrogen atom, suffix we are using is aza, and if sulfur atom is present, then we using as a suffix thia. So here during the systematic name, in this particular structure there is a nitrogen atom involved in the heterocyclic aromatic ring, and therefore we can call it as aza, plus it is an unsaturated compound, and unsaturated compound 5-membered, we know that OLE is a suffix used there. Or this nitrogen atom, or we can call it as a azole of this compound, or we can call it as hydrogen atom. It is a saturated at one position, so we can also call it 1H azole, 1H azole. Either you can say azole or you can say 1H azole. That is a systematic name of this compound, and how that systematic name is given to that heterocyclic compound we fully explain in our previous lectures. So now today we are going to discuss about the synthesis of pyrrole. Let's see synthesis of pyrrole here. synthesis of Pyrol. Synthesis of Pyrol. Who synthesize this compound first in the laboratory? So name is given to that synthesis. The name of that synthesis, the scientist name was given to that synthesis. The name of that scientist is Polynuclear synthesis. Polynuclear synthesis, we can call it. What he did, he synthesized this compound in the laboratory by taking very simple starting compound which is readily available in the market, and the another compound is, or the catalysis we can say, inorganic material compound he has taken, or we can say here from 1,4-diketone similar to furan. The pyrrole can be obtained from 1,4-diketone, or we can call it acetonil acetone can be used as a starting material for the synthesis of pyrrole, and which is known as Polynuclear synthesis. Observe the spelling AA, Polynuclear synthesis, KNORR, Polynuclear synthesis. Starting from 1,4-diketone, which is also known as acetonil acetone. Acetonil, here is a not Y, E. Acetonil acetone, on heating with ammonium nitrate at 100 degrees centigrade gives 2,5-dimethyl pyrrole. So what he did, here he has taken acetonil acetone, on heating with ammonium nitrate at 100 degrees centigrade gives 2,5-dimethyl pyrrole. This is the simplest procedure for the synthesis of pyrrole that we have mentioned here. Now the chemical reaction which I am going to represent here, you can take the starting material. The starting material is this one. Here you can show CH3. The name of this compound is, Here 1, 2, 3, 4, 5 and 6. At 2 and 5 position there is a dione. So 2,5 hexane, dione. You can call it as acetonyl acetone or 2,5 hexane dione, not dione. Dione, IUPAC name, and the common name as we know that, which is written here, acetonil acetone will be treated with NH4 twice CO3, which is known as ammonium carbonate, at 100 degrees centigrade heated, and it gives the compound, the product form, this one N, then H, one methyl group here, another methyl group here. And as we know that the systematic way numbers start from heteroatom 1, 2, 3, 4, 5. So look at 2 and 5 position, there is 2 methyl groups are present. So you can call it 2, 5. So 2 are there. So you can use di. 2 means di, identical alkyl groups. So 2,5 dimethyl pyrol. So that is the name of this compound, and we have synthesized here very simple way how they prepared this compound in the laboratory. They had taken as a starting material acetonyl acetone. On heating with ammonium nitrate, which is an inorganic material, at 100 degrees centigrade gives 2,5-dimethyl pyrrole, and which is represented here. The chemical equation is written over here, and this is a starting material. This one is called as ammonium carbonate. I think ammonium carbonate, not the nitrate. Make the correction here, ammonium carbonate, which is an inorganic material they have taken for the synthesis of 2,5-dimethyl pyrrole. The name of this compound is ammonium carbonate. Name of this compound is ammonium carbonate, which is a material they have taken for the synthesis of this pyrrole. And now once you have synthesized this compound pyrrole, now let us talk about the reactions of pyrrole. Let me clean the board first, and then we have synthesized this pyrrole by using Polynuclear synthesis. Polynuclear synthesis is a very famous reaction for the synthesis of five-membered heterocyclic compounds. Now let's move on to the next point, which is reactions of pyrols. Reactions of pyrol. Reactions of pyrol that we are going to study here. Similar to as a furan, pyrol undergoes electrophilic reaction at two position. I am highlighting the word two position, which is very, very important. Essentially, why these undergoes electrophilic substitution at two position? The answer could be, see here, this is a pyrol. Suppose E as an electrophile. Now the lone pair which is present on that nitrogen atom, which is delocalized in this manner, and the compound which we are getting here, I am showing here NH, double bond, here is a electrophile and hydrogen atom. Now observe this transition state carefully. Here the positive charge I am putting on nitrogen atom. The reason behind it, this nitrogen atom exceeds the bond. Normally nitrogen shows a 3 bond. Here are 4 bond, 1, 2, 3, 4, and therefore positive charge present on it. Now we can show the resonating structure over here. After aromatization back, this proton can be lost here, and this double bond form here, this double bond shifted here to here, and that lone pair coming on its original position, and finally you will get the structure which I am representing here. Here is a electrophile which is present at two position. And why pyrol undergoes electrophilic substitution reaction at two position? I hope you might got the answer of this question. So that is the reason why pyrol or 5-membered ring generally undergoes electrophilic substitution reaction at two position. That would be the main reason. Essentially, the common reactions shown by these 5-membered rings are in previous molecule or the compound which we have considered furan. There we have seen the common reactions given by that furan are sulfonation, Friedel-Crafts acylation, diazocoupling reaction, Rimmer-Tymon reaction, and the hydrogenation reaction. The same reaction we are going to carry out, only the starting material is here different. In that case is a furan, but in this case is a pyrol, and these are the 5 main reactions we are going to discuss here. Let's start with first one, that is a sulfonation. You got the answer why pyrrole undergoes electrophilic substitution at 2 position. The answer is hidden, and it reveals that those are knowing the concept of resonating structure. I hope you might got the answer of this question. Now let us see first reaction, which is a sulfonation. Sulfonation, and similar to as a furan, pyrrole undergoes pyrrole on sulfonation with SO3 in presence of pyridine gives a pyrrole to sulfonic acid. Concentrated H2SO4 cannot be used as pyrrole undergoes polymerization reaction. So the reason is slightly different in case of furan and in case of the pyrrole. Sulfonation of furan cannot carried out in presence of concentrated sulfuric acid, as it opens the furan ring, and hence sulfonation of furan is carried out with sulfur trioxide and pyridine. Listen carefully here also. Pyrrole on sulfonation with sulfur trioxide in presence of pyridine gives a pyrrole to sulfonic acid. Concentrated H2SO4 cannot be used as a pyrrole undergoes polymerization reaction. And as we know that polymerization means polymer type, one of the basic unit attached to another unit, and there will be a longer chain or the complicated molecules, very high molecular weight of that compound becomes. So that type of the reaction are generally known as polymerization. And here pyrrole on sulfonation. Pyrrole on sulfonation, pyrrole on sulfonation with SO3 sulfur trioxide in presence of pyridine, gives pyrrole to sulfonic acid. Concentrated H2SO4 cannot be used as pyrrole undergoes polymerization reaction, polymerization reaction. See here, sulfonation, pyrrole on sulfonation with sulfur trioxide in presence of pyridine gives pyrrole 2-sulfonic acid. Concentrated H2SO4 cannot be used as pyrrole undergoes polymerization reaction. Let's see here, the starting material is a pyrrole. The structure of pyrrole, which I have shown over here, is the structure of pyrrole, and it will be treated with SO3 in presence of pyridine. SO3 in presence of pyridine, that the sulfonation reaction takes place. Sulfonation reaction takes place, and the temperature is once again 100 to 110 degrees centigrade. The reaction smoothly takes place and giving high yielded product, that is SO3H. This is a compound, that is a pyrrole 2-sulfonic acid. This is known as a pyrrole 2-sulfonic acid. 2-sulfonic acid, which is a product which we have got in this case. So remember here, these are the some of the reaction we have discussed in these lectures. So polymer synthesis we have described. According to that, we got pyrrole, and after synthesizing that pyrrole, we discuss some of the common reaction of that pyrrole, and pyrrole generally undergoes electrophilic substitution reaction at 2 position. Why 2 position? We draw the resonating structure or the canonical structure, and from that we know that the transition state form, which is a more stable one, and that's why we are getting the reaction at 2 position, electrophilic substitution reaction. And later on we will see some of the selective nucleophilic substitution reaction with those 5-membered ring as well as 6-membered ring. In our next lecture, I think with this, the rest of the reaction of pyrrole, like Friedel-Crafts alkylation, diisocoupling reaction, Riemer-Tymard reaction, hydrogenation reaction, these are the reaction with that pyrrole we will discuss in our upcoming lectures. Till then, have a nice day. Thank you.